trying to do. I initially talk a little bit about the industry itself, a little bit about the innovation in the industry, then about what KLA is doing specifically in this space, and I will pivot over to a use case in automotive segment where we have gone not only to our customers, but customers, and a third level customer. We have been able to integrate this whole value chain and figure out a way to create value for the whole chain. So what seemed like impossible actually happened. So that's an example for collaboration. So that's a way for me to invite further ideas to collaborate. So another question, just to get the pulse of the audience. How many of you figured out at least one person to connect to offline that you said, I want to follow up with this person, I have something to ask or I have something to connect? You figured out one person to connect to. Okay, few hands, 10%. So yeah, there's some. But I hope I'm able to offer something that we feel there's something to connect to. How many of you figured out one action item? You learned something from the sessions and you picked up one action item that you think you'll go and do something about it. There's about another 20% of hands going up. Okay, thank you for that. So we'll get started. So really these are the 4 things I want to impress upon you. Our industry, the semiconductor industry, the chip fabrication industry is what I'm going to talk about, has been driven by innovation. And KLA's innovation, I'm thankful to Applied Materials and Lam's presentation. They brought into focus the equipment industry, so I'm going to build on that. Drives the digital era. And this industry where we make equipment, so I'll talk a little bit more about specifically what KLA does, but we are in the broader equipment segment. We need super high precision electronics parts that form part of this equipment that we make. Some of these equipment sell for anywhere between $1 million up to $35–40 million each. These equipment sometimes ship on a single Boeing 747 flight, and the largest equipment we make takes 7 such flights to be shipped. So these are pretty involved machines and requires a lot of parts and a bill of material. So we need that ecosystem for us to be able to start manufacturing in India. But while that is still happening, can we already build on our strength? Can we lead with what we are already good at? And we are beginning to do that in India. So lead with our AI, algorithms, and software. That's really what I wanted to cover. This is something that all of us have seen. There's been a steady increase, and we are in this phase of digitizing everything, and that's driving our demand. The only number that I would want to point out is for 2030, we are growing at a 7% CAGR. The whole industry value chain is growing at that rate. That's a very healthy rate for us to count on. In spite of the geopolitical issues, in spite of the market fluctuations, this is a demand that's here to stay. And another major vector in motion right now that we are all acutely aware of is the nationalization or localization of demand, where everybody wants to take care of their supply chain and produce locally. There's a whole amount of committed demand. India is still not showing on our map. As soon as a fab groundbreaking happens, then India will show up here. But there's a lot of nationalized demand where semiconductor is going to be manufactured, so there's good opportunity. So now, let me pivot to the innovation piece. Anyone who has been in the chip fabrication space knows Dr. Gordon Moore, a person in Intel who predicted a long time back, saying in every couple of years or so, the number of transistors in a chip will double, and the space it will occupy will become half. Not only that, over the time, things have become faster, cheaper, smaller, to the extent from 1971 to 2017, the chip has gotten 4,000 times faster, 5,000 times less energy consuming, and 50,000 times expensive. So just to put those numbers in context, if only any other industry were innovating at the same pace, automotive industry, a lot of our friends spoke here, the engines would be the size of an ant by now, if you had innovated at the same pace. A large housing complex would cost the size about a cupcake. That would be nice, right? And the time it would take to fly from New York to Paris would be just about the time you take to click your seatbelt. You would have gone. That's the magnitude with which the semiconductor industry, semiconductor manufacturing has gone ahead. So this is the entire chain, and I want to take a bit of moment to say, so there is substrate. This is blank silicon wafer. That's where the world starts for us. And there are reticle, what we call as a glass plate, where the circuit to be printed is put on it. Okay, and this circuit gets printed on this wafer. This happens in a different factory. It's called an integrated circuit factory. So somebody like an Intel, Samsung, Global Foundries, Texas Instruments, these are the folks who own the factories, fabs, where this is being printed, right? And these are our primary customers where we supply equipment to. But further along the line is where the wafer gets cut out and packaged and built into components, and finally they get integrated into flat panel displays or printed circuit boards, then ultimately get into several of these end segments. Okay, so the reason I showed the whole value chain is KLA has products in this whole segment. Every step we have multiple categories of products. Sometimes, overall it's about 100 plus categories of products that are there to service this whole segment. So we have a broad portfolio where we can collaborate pretty much on any of these spaces. Okay, so the opportunities are pretty wide. So let me now get to very specifically what KLA does. This is a highly magnified view of, at a transistor level, what is getting printed. And I don't know if you noticed the cell phone in your pocket getting warmed up, like as though you had a very heated conversation. It's really not the heated conversation, it's the chip leaking power there, right? So you don't want that. That's usually driven by defects like these. So when the defects are so tiny, and since morning you've been hearing, you're operating in a few nanometer space, and each of these defects could be like a nanometer or less. You're basically looking at a few molecules, right? So when you want to find defects, you can't fix these if you can't find them, if you can't see them, and you can't control them if you can't measure them. That's what our customers like Intel, TSMC, Global Foundries, that's what they have to deal with, right? So we come in to find these defects and variations. That's really what KLA is. We make equipment to look for these defects and variations. So this is a typical KLA machine. This is what it looks like, a wafer that goes in. Eventually, what comes out is a defect map. We would have located billions of pixels that are defective pixels for every micron, every 100 micron square. So that's the amount of information we are able to glean off this wafer and find out where the defects are. And the defects would look something like this. When you get into a high resolution microscope, you'll be able to spot the defect, right? And out of the billions of pieces of information we get, we need to filter out things that don't make sense and come up with a defect of interest that actually matters. Okay? So basically KLA is involved in process control, and if you don't do process control, a factory that manufactures chips, for every 100 chips, about 40 to 60 of them would go defective and be thrown away. So a typical factory that's ramping up its production, this is where it would be without process control. With process control, you're able to shift leftwards, basically saving money, and saving time, you're able to ramp faster. Okay? And every 3 months you're able to move the curve left, it's a big deal. If Samsung ships their mobile phones 3 months later, what happens? China would have made another phone and the market is gone. So our customers lose market in months. So every month saved here would mean a lot to our customers. So that's where we come in. And this is an example of inspection and metrology, where we are able to find the defects with no a priori knowledge of what is on the wafer. It could be any one of the devices that you guys are making for your automotive. We wouldn't know about it, but we'll figure out what the defects are, or we measure to say what's going wrong. So those who are from algorithm background, it's basically outlier detection, and we have been doing it ever since. And the most recent one where we introduced deep learning based. We hear a lot about AI, and we've been hearing that since last evening. But only when you take AI implementations to production, you realize it's easy to create an AI that works in a laboratory. But when you take it to production, it just doesn't scale. It doesn't work. It's not that easy. How to get something that is AI-based into a production has been a challenge, but we have learned it, we have perfected it, and released it to our customers. Similarly, AI-based systems, we released it in 2017. That's deep learning based to make accurate measurements. So that's where we stand. And so you might ask, okay, so where is the new range of? I mean, you understand we solved the complexity in the past, but what's changing? What's changing is the methods that our customers are using to make these wafers. The gate-all-around is the technology that's coming in, 3D NAND, and one more is the EUV lithography. Basically, our customers are always figuring out how to make the chip with a different material, how can I get a little bit more efficiency in the chip. When they do that, it changes everything. The type of defects that show up changes, and the size of the defect changes, the material properties changes, the way it looks changes. So we have to change all our methods of finding these defects. So, bottom line, we are operating across the whole value chain to be able to support inspection and metrology in each of these segments. And eventually these chips get into all kinds of applications that we saw, including the automotive that we just spoke about. So, quick summary. KLA, founded more than 40 years ago, headquartered in Milpitas, about 30,000 employees, making about $8 billion a year. Very strong DNA. The company's core DNA is about physics and math. That's really the DNA of the company. We saw some other equipment companies this morning where the DNA is a lot about chemistry. This is about a physics and a math company. So I show this picture with a lot of pride. This is what goes into the guts of making such a machine. If I were to simplify it and use very simple words to describe, it's a super high resolution microscope. Just a bunch of robotics and precision electronics guiding it to go find the defects on these wafers. But you can imagine every imaginable high-tech engineering space gets involved in making such a machine. So, really, what's our secret sauce? Our secret sauce, these are the core technologies that make KLA's machine the super expensive equipment that our fabs have to depend on. So the light sources, you saw in the video that said, some of our light sources are brighter than the sun. And I said, really, are you sure? And they showed me that on the surface of the sun, the amount of light our broadband plasma tool, we actually have plasma being produced and the light being captured from there, because there's not enough photons that you can actually image with, because the material is moving at such a rate, our machines are able to count how many photons am I actually grabbing. So that's the complexity of the light source. Optics, you have to have the best optics, just like you would put on a Hubble telescope. Very similar, high quality optics have to go into these machines. The sensors, again, custom made, and is our own IP that, very specific vendors in the world, probably right now only one vendor can make it in the whole world, right? So that's the kind of IP that goes into making these machines. And I'm trying to figure out how to participate in this supply chain ecosystem out of India. What can we do from here that can add value into this? So throughout the day, I've been learning from each of the sessions to figure out where can we collaborate with another company and where can we intersect any of these technologies. One area that we can readily intersect, and I'll show you an example, is the image processing, data processing, algorithms, and AI. So in that particular space, we use AI for our own machines to make our product better for inspection and metrology. to make the chip manufacturing better, which produces better chips, faster chips, which gets into high performance computing, which then we are able to take advantage of and build a better AI system. So it's a virtuous cycle that we are able to build and take advantage of. So that's a pretty neat circle of life that we complete with AI within our own company. And you can see that this would benefit the whole industry at large. Right? The quality and reliability is absolutely needed. And one conspicuous group that's missing from this space is automotive, right? Since we've been talking about automotive, I thought I will use that as an separate example. So, I think we all can relate to having an automotive that has semiconductor in it that is defect-free, right? We put our family, we put our whole life into it, and we want it to be absolutely defect-free. The whole automotive ecosystem is working super hard. Why do they use 40 nanometers? We just heard prior panels say 40 nanometers. Why? Because that's more reliable. Your 3 nanometer is all cool, but it doesn't give you that level of reliability. Anyway, so for that level of reliability, typically when the process control happens, a lot of defects do skip. Eventually they may be caught in the electrical testing phase, but some of them even skip, and ultimately a defective chip, a latent defect gets introduced into an auto segment. We don't want that. So KLA introduced an AI-based system where we are now able to catch a number of these defects early on so that the escapes are minimal. And the way we do that is we take the data provided by the chip manufacturer, and we work with, our immediate customer is the factory that makes the chip, but the chip will get consumed by an automotive segment. This is an example of collaboration where we started working with the auto segment to figure out how to take this data, interpret it, and catch these defects early on, so that not only our fab customer benefits, but our automotive customer as well benefits. Okay? Final example on reusing our own AI. This is an electron beam-based inspection machine that leverages AI to remove noise that we find in our systems. Let me show you the example of how much noise our system catches, because you're trying to find signals. So this is the defect that is caught, and that's where we're showing defective versus non-defective image difference. This is what a non-AI system will look like. That's the amount of signal we are catching, and we need to be able to spot this tiny defect, ignore everything else going on. Our AI systems are able to learn and suppress the noise, that we are able to highlight only the defects that we care about. That's our implementation that we have shipped to our customers. So it's a lot of physics-based information, optics and light source-based information that goes into modeling this behavior, and finally we're able to adopt it into a product. So that's an example of how we are leading, and this was done in India. So we are able to lead from AI and software and algorithms while we are still developing our non-software hardware capabilities. In the end, I want to leave you with this thought that we created a dedicated team, a research team that works on algorithms, on accelerating algorithms through any kind of technique that we can. And we set up a team as a research team inside IIT Madras Research Park. When you're there, please do visit. And this team is open to collaborating with many other organizations. We are working with many professors. This gives us a connect with academia as well as industry. So with that, I leave the floor open for the next thing that we're going to do is talk about, the KLA is hosting, Nani is going to host a panel where we're going to talk about co-opetition. The agenda has the word printed wrong. It calls it as competition. We don't want competition. We are of course competing anyway. But what we're going to talk about is how, even as competitors or peers in the market, how can we all cooperate? So the final thing I want to leave here with is we all need to develop some things, scale some things, lead and collaborate. So we want to develop parts and supplier ecosystem in India, which we and our customers can benefit. So we are open and always looking for opportunities to do that. We have the world class, we have the talent, but we need world-class talent in high-precision engineering, systems integration, optics, light sources, and so forth. So we need to be able to scale that from small labs to production scale. We need to be able to lead. We already are top of the line. We need to not shy away from leading the world with that, and finally collaborate amongst ourselves to establish standards, govern flow of information, find new use cases, that we create something unique that the headquarters has not told us, but we have figured out, and we are able to create something that we can go back to the headquarters and say, that's something we have done, and we are able to do it independently and deliver value to our customer and to our headquarters. So with that, I'll leave the floor open for our panel discussion, where we're going to talk a lot more about how we can collaborate. Thank you.
Thank you, Mr. Dominic. And to do the felicitations, I would like to request Mr. Sunny Malhotra to step onto the stage. I'm surprised that you said in the agenda there is a mistake, but I saw it twice, which is there as co-petition. Okay, it should not be read as competition. It's a very interesting word with this point.